Alrighty, hi everyone. Welcome to your first exam review. My name is Allison, if you don't know that yet. But I will usually be doing one of these Zoom sessions before each of your exams. So hopefully this is a good start to kind of see like how I'm going to run these types of things. This hour will be for you. And so as you continue to write stuff, what you want to do in the chat, I can try and cover as much of that as possible. I also have some practice questions for you, like an extra document like I did for your last quiz. So I will send that out along with the answer key later tonight. But you'll be able to get the practice problems first, and then you can check your answers later on. I won't have the answer key ready just yet. I think I'm just going to go off of based off what's in the chat. If you have any questions along the way, feel free to write them in the chat. Feel free to unmute yourself. This is going to be very interactive, so I want to tailor this hour for what is going to be best for you. So if anything doesn't make sense along the way, or if I'm moving too fast, please just let me know and I'd be happy to explain that a little bit further. But I'll just kind of go in, look at what the chat is going on, and kind of get started from there. So I think what we didn't talk about too much in class is percent abundance and limiting reactant. So I want to start there first, if that's okay with people. And I'll kind of do this where I will give you a couple of like pointers and what to look for in a question, and then we'll do a practice problem to kind of practice what this type of question would look like. Okay, so to start off, if we look at percent abundance, or not percent abundance, excuse me, percent yield is what I wanted to say, is what we haven't covered too much in class. This is going to tell you is how much your reaction succeeded. Okay, this is usually experimental data. And you can do a limiting reactant question first before you find out what your percent yield is. Okay. Does anyone know the formula for a percent yield question?
Is it actually you divided by theoretical?
Yep, perfect. Yep, awesome. So percent yield is going to be actual over theoretical. And then we're going to do times 100. If you're given a percentage, then you need to multiply it by 100 at the very end. But it will be a decimal of some point. Can you get above a 100% yield?
No, because you wouldn't be able to create more than what you put in.
Okay, I like your thought there. So usually we're not going to be able to see a over 100% yield because we can't create more than we have. But sometimes we do see it above 100% yield. Some of you might see that later on in your lab experiences. This just might be from impurities or other stuff along the way. So you don't necessarily have to be below 100%. But it's usually typical that we see less than 100% for your percent yield. Okay. When we talk about our actual and theoretical yields of things, what is our theoretical? Where is that determined from? Does anyone know?
You just take the advanced chemical formulas and plug in according to the numbers of moles, and we put in and see how much we should get out of it.
Yeah, awesome. Right. So your theoretical yield is usually determined from your question or from your given materials. Okay, so if we had a question that says, we have, right, if we go back to our sandwich questions, if we have 10 pieces of bread and that's going to be our limiting reagent, how many sandwiches can we make? It's going to be 5, like how we talked about in class, right? So that would be our theoretical. We expect to see 5 sandwiches that are made. However, if we come up with 4 sandwiches for whatever region, that would be our actual yield, right? So our theoretical is what we expect to see, and the actual yield is what we actually see after we do our experiment, okay? So I guess usual theoretical is what we expect to see. And then our actual will be like what we got in lab or what we observe in lab. Okay, any questions on the differences between actual and theoretical yield? Okay, so if we were to talk about a percent yield question, you might say, okay, so we might have a question like this. It says 1 mole of sodium hydroxide and 1 mole of HCl react. How much water is expected to form? Okay, so what type of question am I actually asking you here at the start of this? Does anyone know what kind of question this is? Maybe help us. Good. So it's an acid-base reaction. Absolutely. So this is acid-base type of reaction. But we are given 1 mole of our starting materials each, and then nothing about our products. So this is actually a limiting reactant question to start off in the beginning. Okay, so you might see this type of question asked first when you're trying to find percent yield, because you need to know how much you expect to see first. Does that make sense? Any questions there? Okay. So and we won't have to solve this one right now. We'll come back to this later, but you might see this one first in a percent yield. So an actual percent yield question might look something like this. Okay. Okay, so we could say if 5 grams of sodium chloride is expected to form from an acid-base reaction, but 3.63 grams is collected, what is the percent yield? Can anyone tell me how they would set up this question?
Would you put the 3.63 on top and then do we?
Mm-hmm.
And oh yeah, and then the 5 grams on the bottom times the 100.
Awesome. Yep, so your percent yield will be equal to 3.63 grams on top divided by the 5 that we expected, and then multiplied by 100. So what does that come out to be?
72.6%.
Awesome. So we have 72.6%. We want 3 sig figs because we started with 3 sig figs in our original question. And this looks good to me. Okay, what questions do we have about percent yield? Does this make a little bit more sense? We kind of rushed through this at the end of class. Okay, awesome.
I have a quick question.
Yep, go ahead.
Are the questions about this topic going to be like where we're given the actual and theoretical? Because I know in the homework we had to first find the theoretical and then calculate the percent yield.
Yep, so she could, for like a short answer type of question, follow that same homework format. But for a multiple choice question, she'll probably not have you find both the theoretical and the actual, something like along those lines, just because those tend to be a little bit shorter of questions. But I would know how to do both. And then in the practice problems that I do have one where you have to find the theoretical first and then use that in your question. So I would expect to see both. If you know how to solve finding the theoretical first and then percent yield, then you're golden.
Okay, thank you.
Yep, of course. Yeah, so we can do 15 on the mock exam. Let me see. Okay. So we can kind of go over this one. Is there anyone that hasn't done the mock exam yet? Okay. So if you haven't done this question yet, you could do this right now. But we'll kind of talk about it, and then if you have done it, then we can kind of go over it. You can see if this makes sense. Okay, so for 15, we have using the balanced chemical equation below, what is the actual yield in grams of oxygen when 27.4 grams of potassium chloride and decomposes to the percent yield, and the percent yield is 81.4%. So you want to, you're looking here for your percent yield or for your actual yield, but you're given percent yield this time. Okay, so it's slightly different, but whenever I write something for, or whenever I'm taking an exam or following a question, I always like to write down what the formula is that I'm going to use for it. So for this one, I would say percent yield is going to be equal to your actual over your theoretical. And we know our percent yield. We don't know our actual. And then the theoretical we can find given our question. Okay. Okay, so when we're looking at this question, we have our 27.4 grams of potassium chlorate. We know that this one's going to be our limiting reactant because there's only that reactant. And we're looking, but we're going to look to see how much of our oxygen we can form given that 27.4 grams of potassium chlorate. So what's the first thing we have to do?
Convert from the grams of potassium chloride to moles.
Yep, awesome. Right, so we're going to take 27.4 grams of potassium chlorate. I guess this is chlorite, excuse me. And we're going to convert that to moles. So where is moles going to go, on the top or the bottom? Awesome, yep. We're going to have 1 mole of potassium chlorite will be equal to the molar mass of potassium chloride, which she gave you as 122.55 grams. Now that we're in moles, what can we do?
You'd use the mole ratios, right? That
Yep.
are given in the balance equation.
Awesome. So you're going to use the mole ratios given from your balanced equation. Your mole ratios come from your coefficients in your balanced equation. So that's going to be 2 moles of potassium chlorite to every 3 moles of oxygen. Where does oxygen go? Does that go on the top or the bottom?
Top again.
It goes on the top again. Awesome. So 3 moles of O2 will be equal to 2 moles of KClO3. Do we need to do anything else with our moles of oxygen?
Convert from moles to grams to get the theoretical yield.
Yep, perfect. So we're going to convert from moles to grams. So 1 mole of O2 will be at the 32.00 grams. And how many grams of oxygen does that get us?
10.732.
Awesome. Okay, does this stop? Is this where our question will stop? Nope. So now we need to use this theoretical yield, right? This is our theoretical yield. We're going to use our theoretical yield, and we are going to use that in our percent yield equation. So we're going to say percent yield. What do I plug in for percent yield? 81.4 or 0.814?
0.814.
Awesome, right? We'll have 0.814 is equal to X, because we don't know what our actual yield is, over 10.732 grams. We can cross multiply over here. So X will be equal to what?
$8.74.
Awesome. Okay. That's grams of O2. I don't know what the third decimal, what's the third? Okay. So how you round is a good question. So you start off with 27.4 grams of potassium chlorite. So your final answer, so that has 3 significant figures. So your final answer should also have 3 significant figures. When you find your grams of oxygen as your theoretical yield, I would give yourself a couple extra decimal points there, because that way you have the little bit more accurate answer. So if you use 10.732, I think that's a good number of significant figures to keep, and then you can round to 3 at the very end. So if 15 is the type of question you have, if that's a short answer, then you might get some partial credit there. For multiple choice, there will not be any short answer, or there will not be any partial credit. I don't know how the electronic exam looks/works exactly. So you might get partial credit, there might not be. I'm assuming that if it's short answer, there will be ability for partial credit. Does that make sense? We can't go over 5.
I would believe so.
Okay, cool. Is there any other questions with percent yield or limiting reagent at this time?
No, question 10, I think, uses a limiting reagent.
Yeah, okay, so we can do with this. Let me
Or did
just,
you already do it?
this is when I did it myself. And then question 5. Yeah, okay. So we'll do question 10, and then we can do question 5. Okay. So for number 10, we have, what is the mass of a sample of vanadium 4 oxide containing 40.76 times 10 to 23 oxygen atoms? You want to place your final answer in the box, blah, 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 blah. Okay. So the main question here is this guy here. Okay, and although she's going to give you a lot of your formulas today, tomorrow, you still want to be able to remember your naming. That is something we did in the beginning of the semester, so she can ask you that at any time. And I do have a question in the chat. You will be given your polyatomic ions, so you don't need to know those. So when we have vanadium 4 oxide, this Roman numeral, I forgot the name for that right there. This Roman numeral tells you what charge your previous metal will give you. So if we have vanadium, that will be V on the periodic table. And we know that that will have a +4 charge because that Roman numeral is telling us that it is +4. What does oxide have as a charge?
It's just oxygen
-2.
Yep, so oxygen will have -2. And so what is going to be your formula for vanadium 4 oxide? Awesome.
VO2.
Awesome. This will be VO2. Okay. Questions how we found that? Okay, awesome. So we're looking for a sample of this oxygen atom or the sample of this compound given oxygen atoms. So if we start off with the number of oxygen atoms, you're always going to start with that on top. Okay, how do we get out of atoms? What do we need to use?
Avogadro's number.
Good, so we need Avogadro's number. And so is 1 mole going to go on top or bottom here?
On top.
Good, so 1 mole of oxygen will be equal to 6.02 times 10 to the 23 atoms. Okay, you always want to make sure that your mole and your 6.02 are on opposite sides of your fraction. 6.02 times 10 to the 23 moles does not equal 1 atom or that way around, right? We want to make sure that 1 mole equals a very large number, right? 1 dozen equals 12 things. So we want to make sure that those stay opposite each other. Okay. Questions here so far? Okay, so now that we're in moles of oxygen, what are we going to use in order to find the moles of the compound? Good, we're going to use the mole ratio. So for every 2 moles of oxygen, how many moles of vanadium oxide do we have?
1.
1 mole. Okay, does that make sense how we found that mole ratio? From VO2, 1 mole contains 2 moles of oxygen. So we're just going backwards. Like usually you would say, okay, we have this many moles of the compound, we have this many moles of oxygen. This time we're just going from oxygen to the big compound. Okay, and what's the last thing we need to do to get to grams?
Multiply the moles by the molar mass of VO2.
Awesome. So we'll have 1 mole of VO2 is equal to the grams of VO2. I don't remember what that is. I think this was 38.2, 38.6, something like that. Someone has the math. 82.94. Awesome. Thank you. Somewhere around 32. Okay, 32.6. Awesome. Okay, so 32.6 grams of VO2. 32.6, somewhere around there. Okay, questions on this one. Slightly different than a limiting reactant or percent yield, but still important. Any questions here? If not, we can go to 5. Okay. So for number 5, this is a limiting reactant question. So that's a good question, Sam. So a limiting reactant is going to be, what do I say, like the slow point, or what determines how much product can be formed. Okay, it's something that you have the least amount of. And so that's going to indicate how much of a product that you can produce, because whatever is the least amount of reactant is going to it's going to dictate how much product you can form. We kind of started, but this is like our first like actual limiting reaction question. Okay, so when we look at this question, we have how many moles of the precipitate is formed when 4.21 moles of your silver compound is reacted with 2.76 moles of barium oxide. And we are looking at an unbalanced reaction. So what's the first thing we need to do whenever we're given a chemical reaction? Awesome, right? So we need to balance the chemical equation first. Does anyone know how we need to balance this?
The procedure or about like actual
Just the coefficients is fine.
I don't know.
So when I'm looking at this, I see that your C2H3O2 is in this reactant here, and then only in your product here. So I see that I have 2 here, so I need a 2 up front. That means I have 2 silvers now, and so I need to make 2 silvers over here. And then that 2OH balances out the 2OH from your reactant end product. Yeah. Awesome, perfect. Okay, we need a balanced equation because that's going to determine our mole ratios. So even if you're given a balanced reaction, you want to make sure that it is balanced and she's not just like kind of screwing with you or anything, okay? Or, you know, something didn't load properly. You just want to make sure that it is balanced. Okay, so when you're doing a limiting reactant question, we want to check both of our reactants against a product. So we want to see out of our 2 reactants, which one will produce the least amount of a specific product. You want to pick the same product for both of your reactants. Here it's asking for how many moles of the precipitate is formed. So I would pick my precipitate as your product that you're looking to check on. How do we know which one is the precipitate?
The
Good.
one.
Go ahead. Okay, so the one that's going to be solid is going to be your precipitate here. Okay, that's always the case. The precipitate will always be a solid. So the first thing we're going to do is we're going to check our silver compound. So we'll say that we have 4.21 moles of silver H2H3O2. And how do we get to moles of our product?
Yeah. Well, it's the same.
The ratio of moles.
Yep. So it always comes down to the mole ratio, right? So we'll say that, what's our mole ratio here?
2 to 2.
Good, it's 2 to 2. So we'll have 2 moles of AgOH is 2 moles of AgC2, blah, blah, blah. Okay. So that comes out to just 1. So we know that we're going to produce 4.21 moles of our AgOH if we used up all of our original silver compound. Right, so AgC2H3O2 was our limiting reagent, we would produce 4.21 moles of silver oxide. So we're going to know the mole ratio because that's coming from the coefficients in the balanced reaction. So that's the 2 here and the 2 here. Michael, we don't know that 4.21 is limiting yet. We're just saying that if it were to be the limiting reagent, then that would be how much we produce. We still have to check the other reactant first. Okay, so our other reactant is going to be 2.76 moles of barium oxide. Again, we're going to use that molar ratio, and this time 1 mole of barium oxide is going to be equal to 2 moles of silver oxide. And what do we get for our number of moles produced here?
5.2.
5.52 moles of silver oxide, or silver hydroxide, excuse me. So which one is going to be our limiting reagent?
The silver compound.
Good. The silver compound, this one up here, will be our limiting reagent because it produces the least amount of your product. Okay, so when someone asks for the maximum amount of product that can be produced, it's going to be this one, right? We can't produce more than 5.5 or more than 4.21 moles. We can't get to that 5 moles because we don't have enough of the other reactant to produce that. Okay,
And,
so go ahead.
Are both of the compounds are both the compounds are interacting with the precipitate, and is that why we're checking the ratio of each to that precipitate?
Yes. Yep. So because both reactants contribute to that second precipitate, or yes, to the precipitate, we need to see if what one we have more of or which one we have least of in order to find the limiting reactant. Good question.
I have a question.
Yep.
So whenever we're looking for the limiting reactant for the precipitate, is that limiting reactant going to be the same for the other product as well for BaCH3O2? If we were to
Yes.
find the moles for that? Okay.
I believe so. So I believe your limiting reactant is just going to be your limiting reactant. You can check that though as well. So if you were asked for the liquid compound in this case, then you can just solve again for the barium acetate or whatever that is on the other side.
I have a question. For the if we were to find the grams for the precipitate, will we just multiply it by its molar mass?
Yes. Yep. So if you had to find the mass of the precipitate that was formed, you want to solve for your moles first, and then you could take the 4.21, moles and multiply it by the molar mass of the silver hydroxide. Does that make sense, Jasmine?
Yes, it does.
Okay. Yep. And so if you're asked, that's a good tip as well. If you're asked to find the grams of the precipitate from your limiting reactant, I suggest stopping at moles first, because whatever is going to be your limiting reagent from your moles will also be the limiting reagent if you solve all the way to grams. So if you solve all the way to grams, it's just giving you an extra step in the thing that's not the limiting reagent. So you can stop at moles, see which one produces the least amount of moles of your product, and then you use that least amount of moles to solve for your grams. What other questions do we have about limiting reagents? So your coefficients from your balanced reaction will be determined by balancing it, right? So we said that we had 2 moles of the C2H3O2 compound or we had 2 of them on your right-hand side because of the 2 here. And then we had, so in order to balance that, we need to put a 2 in front of that reactant. We can't make it a superscript, or excuse me, a subscript, because that would change the composition of the compound. We can only say that we need 2 of those compounds. And then that means that we now have 2 moles of it. So in order to know which coefficients to use, you have to see which compound you're working with and which one you need to get to. So we're using the 2 moles of the AgC2H3O2 in this initial portion here, which goes down here. And then you're trying to get to the 2 moles of the silver hydroxide. So that's why you use 2 moles there, because you're using the coefficient that's in front of the compound you're talking about. What other questions do we have? I saw some people come in about question 8. So we can go over that one too.
I was going to ask for 2, 6, and 8, so that works.
Yep. So we can do 8 next. I know that's something a little bit different, something we haven't really talked about too much yet. So when we are looking at copper sulfate, I guess the question here is, which of the following statements about copper sulfate is true? And then Drew, you do need to know your strong acids and strong bases on the test. That won't be given in a table of any sort. So when we're looking at copper sulfate, this is going back to one of your first couple of lectures when we talked about like elements, compounds, substances, stuff like that. And that's going to be how we classified these certain things. So when we talk about, whenever you have these kind of true and false questions, I always like to say whether my statement is false, whether my statement is true, and if it's false, what would make it true. Okay, so when we look at our first one, we have copper sulfate is considered to be an element. What do we know about an element?
Element is listed on the periodic table, which copper sulfide is not.
Good, right? So copper sulfate is made up of a whole bunch of elements, right? Our elements is on my periodic table tapestry here, right? All of those are elements. So it has to be singular in order for them to be considered an element. That's your copper, that's your oxygen, that's your fluorine, all of those like that. Those are elements. So this is made up of 1, 2, 3 different type of elements. Okay, so we know that this one is going to be false. We also know that whenever you have multiple elements together, this forms a compound, right? That's sodium chloride. Even sulfate, just as a polyatomic ion, is a compound. Those are no longer elements. Okay, questions there? Okay, so for B, we have copper sulfate undergoes a physical change when reacted with sodium carbonate to form copper carbonate. What's wrong about this one?
Physical.
That'd be a chemical reaction.
So I heard the chemical
It's not
reaction.
balanced.
I like that it's not balanced too. I think this is supposed to say copper sulfate, but it doesn't matter. But in any case, the problem here is that it's not a physical reaction, it is a chemical reaction. So a physical change means that we're changing the property, not an element. Okay, so if we're saying a physical change would be ice going to water or water going to gas, right? We're changing one of those physical states. While if this was copper sulfate going to sodium sulfate, an element is changing here. And so that's going to be a chemical change. This will now have a chemical, this is a chemical difference between the two. They will have different chemical properties about them. And so this is actually a chemical change and not a physical change. Questions between the difference between the two? Yes, so physical changes would be, so if we said copper sulfate undergoes a physical change when boiled. Right? We know that if something is boiling, it's just going to the gaseous stage. And so the formula is not changing at all. So it looks the same, just a physical change. Good question. Anything else about chemical physical changes? Okay. Copper sulfate is considered to be a pure substance. We're going to come back to this and we're going to explain why D is wrong first. So copper sulfate is considered to be a homogeneous mixture of copper, sulfur, and oxygen. So can anyone tell me why this one is wrong?
Because they are bonding with each other, they're not just lying around.
Good, awesome, right? So when we talk about homogeneous mixture, we're kind of talking about stuff where you have a whole bunch of things, right? So if you have, blueberries and strawberries and raspberries together, that could be a homogeneous mixture because you can pick out the different portions, or that would be a heterogeneous mixture because you can pick out the individual pieces. But if you took all of those and then muddled them all together and made it like a juice, then that would be a homogeneous mixture because all of your stuff in that mixture is the same. But your blueberry isn't interacting with your raspberry or your strawberry. It's just kind of all there together. Here we are forming a chemical compound. Okay, and so when we're forming those bonds, we're creating a chemical reactant or a chemical product, and those are going to be considered to be a pure substance. Any sort of product, any sort of compound will be a pure substance. Okay, does that make sense for this one?
I would say so.
Okay, cool. Any other questions on number 8?
As far as the one for part B, where it's saying it undergoes physical change and reacting with a compound, if
Yep.
we see an answer choice like that, where it's interacting with another compound, can we just automatically assume that that's a chemical change and rule that out?
Yep, absolutely.
Okay, thank you.
Of course.
For letter D, if it had said it was a heterogeneous mixture, would that have made this statement true?
No. So we can't consider a compound a mixture because they are forming bonds. And so that bond formation is what's going to like change its category from mixture to compound. Does that make sense?
Okay, yeah, thank you.
Yep. A heterogeneous mixture, you can think of like a chocolate chip cookie, right? Where you can see the cookie and you can pick out the chocolate chips from it. If we gave you a copper sulfate mixture as a cookie, you couldn't pick out your copper, you couldn't pick out your sulfur and stuff like that. That helps you visually think of it. And then, yes, we can consider a compound to always be a pure substance. If you have multiple compounds mixed together, that's no longer a pure substance. But if you just have a single compound, that can be considered a pure substance. Okay, anything else on this one? Okay. Let me look at what 2 is. Yep, 2. Okay, we can quickly go over 6. So here, greatest similarity, when we talk about different elements, your groups on your periodic table will all be the same. So similarity is in the groups. So group 1, such as lithium, sodium, potassium, those are all very similar. Group 2, beryllium, magnesium, calcium, those are all similar, stuff like that. So going down the periodic table like this, those will determine your similarity between them. Yep, groups are up and down. your periods go across, and then your groups go up and down. Question on 6. Okay, and then I know I saw 14 a couple of times. Let me go look and see what question 14 is. Okay, we can go over 14, and then we can quickly go over 2. That should probably bring us to 12 o'clock. Okay. Okay, I'll try and talk quickly through these next 2 so that we can leave a couple minutes so that you can just kind of rapid fire some questions if you have them. But in any case, so for question 14, we need to prepare a molar solution of chloride ions with a volume of 375 milliliters. We want to know the mass in grams of zinc chloride that you'll need to prepare for the solution. Okay, so when we look at this type of question, whenever we're given a compound and we are looking for ions or anything, we always want to write down what it would look like if it dissolved in solution. So my first thing I'm going to do is say that zinc chloride will dissolve, right, if it's aqueous, as zinc 2+ and 2Cl-. What questions do we have about me writing it like this? How it looked like that, and how I knew it, anything like that. You would need aqueous, but for the sake of time, I'm going to remove it.
Dissolve mean they both just separate from the ND separate from each other?
Yep.
Okay.
Okay, so your zinc is going to dissolve, or it will break apart in solution and form zinc 2+ and Cl-. Okay, so these are in solution. They would have aqueous on them. I think so, but that'll be sure to be on your exam. Okay, I then like to write out what I know from the question. So you need to prepare this molar solution of chloride ions with a volume of 375 mils. So we know that we need to have 0.0482 molar of this chloride ion. Okay, the thing to remember is that molarity, or the capital M, is equal to moles over liters. So if we know that we have 375 mils and we know our concentration, we are able to determine how many moles of chloride ions we need at the very end. Okay, does that make sense of how we can get to moles? We can use our 0.0482 moles over liter, molarity, which will be equal to the number of moles, which we don't know how much we have, times 0.375 liters, right? And this is just that conversion there. Okay, where did I lose people? So far, so good.
Are we trying to make like I'm trying to make like a certain molarity solution that has a volume of 375 milliliter?
Yeah, so like your final volume here is going to be 375 milliliters. And so we need to use that in order to know how much to dissolve our zinc chloride solution, right? So we're going to take our zinc chloride and use 375 milliliters to dissolve it. But we want to know, but we need this certain concentration of chloride ions. So we need to know how much of that to dissolve in the 375 milliliters. Does that make a little bit more sense?
Yeah, it makes a lot of sense.
Okay. So now that we have our concentration in moles over liter, and we have our liters, we can cross multiply, right? And we can say that X will be equal to 0.375 liters times 0.0482 moles over liters. What units cancel out here?
The liters.
The liters. And so we're left with how many moles?
0.018075.
Right? Do we agree? See another answer in there, so I feel good. Okay. So this is saying at the very end, we need this many moles in solutions. We don't need to worry about significant figures yet. We'll do that at the very end. Okay, so now that we have moles of chloride ions, what can we use to get to the grams of zinc chloride? Good. And why are we multiplying by 136 point? So we're not going to do that just yet. Sorry.
Here are the mole ratios.
Yep, we need our mole ratio first. Perfect. So now that we have this number, we're just going to bring it up here. Yeah, 0.010875 moles Cl. We're going to use our mole ratio of 2 chlorine ions to 1 mole of zinc chloride.
If you don't mind me asking, why is that again? Why we use the mole ratio?
So we need to use our mole ratio because right now we're on like our product side. So in order to get to our reactant side, we can only switch between reactants and products, or really anything, through using the mole ratio or that stoichiometry. So in order to get to how many grams of zinc chloride we need to get to moles first. And so in order to get to moles of zinc chloride, we need to use that molar ratio to switch from product to reactant.
Okay, thank you.
Yep. Okay, so now we should have more or less moles of zinc chloride. And yes, stoichiometry is just mole ratio. Good, we should have less mole. So we'll have whatever this is in half. Daniel, yes, that is the moles of chloride, but we're looking for the grams of zinc chloride.
I think he's just referring to that the 8 and the 0 are swapped.
Oh, I'm so sorry. Thank you. So how many moles of zinc chloride do we have?
Zero point 0.009035.
Awesome. Okay, and this is going to be moles of zinc Cl2. So now we can use our moles of zinc Cl2. I'm just going to move this over here because I ran out of space. So I have moles of zinc Cl2 is 0.0090375. And then we can use our molar ratio, and we can do 1 mole is equal to 136.29 grams. Okay, and what do we get for grams here? Awesome. Okay, questions there?
How do we determine the number of significant figures for this one?
Good. So I tend to look at like the first number I'm given at. So here in our 0.0482 moles or molar, you have 3 significant figures. So I tend to just keep that 3 all the way through. And so I'll get to 3 at the very end.
Okay, thank you.
Yep, of course. What other questions do we have? Does this help clear this one up a little bit?
The significant figures, is it different if you don't have like a decimal? Because logically, like if you have like 1000, then I think like according to the rules, it was like the zeros are all insignificant, but logically like 1001 are totally different numbers, so you can't just write 1.
Yep. So if you have something where it's like 1000, this technically is only one significant figure. So if we start off with 1,000 molar, then we would just round this one to 1.0, or excuse me, 1 gram. But if we given 1,000 with a decimal point, now we have 4 significant figures. And so this would turn into 1.232 grams. So yes, it is weird to say that like 1,000 only has one significant figure, but that means that we can only be confident in that first number.
So we still write 1,000 when we 1,000. Sorry, we still write 1,000 when we write 1,000. Just like when we do something like something with a decimal, we only write 1.
Yes. Yep. Okay, any other questions? The 0 before the decimal does not count. Nope. So when we're looking at this one here, we only have 3 significant figures because our significant figures don't start until we get to our first non-zero number.
What if there's a non-zero in front?
So if we had something where it was 1.0482, this would have 5 sig figs, because when we go this way, right, our first one that we get to is a non-zero, and so that's going to count. Does that make sense? Okay, so we have 3 minutes. I do not have enough time to go over number 2, so I apologize for that one. But this is a combustion analysis question. So if you need to review that one, that's the type of question you're looking at. I do have one of these on the practice problems that I have as well. And you can refer back to your notes. I don't remember what chapter that was for. If you need any additional help from chapter 4 or from question 2. Yep, I'm recording this Zoom right now, so I'm going to send it to Dr. Altimos once I can upload it to YouTube. It just needs like an hour to get it back from Zoom. So I'll send the recording and the practice problems out at that time. This is number 4 for that. And then I guess with 2 minutes left, I'll just give you my little spiel. You do have, so for your exam tomorrow, yep, I'll post the exam and the key as well. So for your exam tomorrow, make sure that you eat a good breakfast and you get a good night's sleep. I know that it's very hard right now to determine the best way to study, but from experience, it's not easy. It's not great to cram. Please just go to bed at a certain hour, put your books away. And it's best to just let all the information you have and absorb it. So my current breakfast right now is 2 pieces of toast and yogurt with berries and some turkey sausage. It's delicious. But I love toast. So anything will do as long as you just put something in your stomach in the beginning of the day. It will help your brain out eventually, I promise. For open-ended questions, you should get partial credit. For multiple choice, you will not. For multiple choice, you will have, right, the answer is somewhere on that screen. So give it your best shot, use it the best to your ability, and ask you for a least or greatest, or an extreme type of question. It will never be the middle answer. It will be either the highest or the lowest. And take your time, work efficiently, make sure you know your formulas, and you will be given a formula sheet. You will be given your solubility sheet. You will be given your polyatomic ions, but you make sure you know your naming rules, make sure you know your acids and bases, and I think that's it. If you do have any questions, feel free to email me tonight. My email is allison.getz at tamu.edu. I will be watching the Super Bowl, so if I don't get back to you right away, it's just because I'm watching football. And then, but I will respond in the morning at the very latest before your exam. So if you send me an email, I will respond before your exam. Okay, I think that's all I have. If you have any questions, please let me know. But at that, I'll wish you very good luck studying, and
Thank you so much.
thank you so much.
Thank you for your help.
Thank you so much.
Thank you. Have a good day.
I did have a quick question real quick. I'm sorry.
Yeah.
So whenever we're doing balancing equations, even if the question doesn't specify that it wants like the least common multiples in front of it, if we get something that's like it's divisible by 2 or like divisible by 3 or something, should we always just assume we should do that?
Yeah, so you always want it in the least, in the lowest possible. It won't affect any of your stoichiometry if you do like balance it and forget to divide by 2 or something on your exam. It won't affect your answer in any way, but it's just easiest for numbers wise to get into the lowest possible.
Okay, thank you so much. I really appreciate
course.
you setting all this up.
Of course. Good luck. Oh, no problem. Good luck.
You did say that for the multiple choice would be the most or the least of something, correct?
Yeah, so if there's an extreme answer, it's like what's the most, soluble or what's the least soluble, it'll never be the in between, right? If you have like 1, 2, and 3, 2 will never be your most or least because that's in the middle, right? It'll either be 1 or it'll be 3.
Yeah. Oh, I have one quick question.
Yep.
It was basically off chapter 3, and it was based off like one of the learning objectives, and it was writing and balancing chemical equations for like the 3 types, like strong, weak, weak, strong. Are we supposed to be able to write or like identify weak acids and strong acids, or like will it be given?
Yeah, so as long as you know your 6 strong acids and 6 strong bases, anything else is considered weak. So if you know what a strong acid and strong base when they react together will look like in terms of a chemical equation, then you know that if it's not that, then it has to be a weak acid or a weak base. And then I think that's what you should know or consider for those there. So I would know your strong acids really well and strong bases really well, because then everything else is considered weak.
Okay, and the strong bases are like the Li. Is it LiOH or like LiNa, lithium, sodium, potassium, calcium? Those like 6, and do they all have OH afterwards?
They all have OH after them. Yep.
Okay, cool. Thank you so much. I appreciate it.
You're welcome. Of course. Good luck.
I had a quick question.
Yep.
Just on like there was the chapter 3 section where they give you percents by weight, and then they're like you have a remainder of this certain element, and then you have to write the empirical and molecular formula. That whole process just kind of confused me a little. Is there a way you could like just kind of explain it a little more, please?
Yeah, so that one you're looking at like percent composition based off of weight. So you're just kind of comparing like what the weight of that element is in comparison to the rest of the compound. So if you have CO2, right, oxygen is going to weigh more than carbon, and you have 2 of those. So oxygen is going to make up more of that weight than carbon will. So you just kind of compare, right? Like if you still need to find the percent composition of carbon in CO2, then you just divide your molar mass of carbon, which is 12, by the molar mass of carbon dioxide, which would be 44. And that would give you a percent composition of carbon in CO2. So then if you need anything else, then you could just work backwards if you're like given percent or something like that.
Okay, thank you.
Yeah, of course. Okay. I think that's it. I'm gonna hang up now. Okay, cool. Thank you all so much. Good luck. Send me an email if you have any questions.
Thank you.
Thank you.